Hey everyone, hopefully you can use these solutions to help you get through the homework. So for the first one, I've written down the 25 work that we did in class. We've got a matrix A. We found the basis for call A by finding the pivot columns of a ref form. I then went another step and got it into a ref form, and I augmented with zeros. So the next step is to find the basis for the null space, which are the solutions to ax equals 0. So we've got to write our solution in parametric vector form and then take the vectors that we see from that. So x1 equals negative 7x4 plus, oh, I'm sorry, that would be x5 actually. Negative 7x5 plus 2x3. x2 equals 1/2 x5 minus 5/2 x3. x3 is free. x4 is negative 4x5. And then finally, x5 equals x5. So with two variables, we know that our null space is going to have a basis with two vectors. So writing this in parametric vector form, we've got x5 with negative 7, 1/2, 0, negative 4, 1, plus x3 times 2, negative 5/2, 1, 0, 0. Just so I don't have to rewrite these again, I'm going to call this vector u and this vector v. And so the basis for null A is equal to the set of vectors u, v. And I'm just going to check that real quick. Yes, that is right. Okay, so the basis for null A has two vectors in it, and the basis for call A has three vectors in it. And just to preview something we're going to do next time, notice that the sum of 3 and 2 is 5, which is the number of columns in the original matrix A. All right, our next problem is 27. Let's have a look at that one. Okay, so in 27 it says construct a non-zero 3 by 3 matrix A and a non-zero vector B such that B is in call A, but B is not the same as any one of the columns of A. Okay, that's easy. So here's matrix A. I'm just going to put 1, 2, 3, 4, 5, 6, 7, 8, 9. And we just need to construct a vector B that is a member of call A. So B just has to be a linear combinations of the columns of A. So I'm going to say, let's let B be A1 plus A2. So AB that would work would be the vector 5, 7, 9. 28 is next. It asks us, construct a non-zero 3 by 3 matrix A and a vector B such that B is not in call A. Okay, so we can take the same matrix as above. Let's just use that. And now we want B to not be a member of call A. I think we could accomplish this pretty easily by just adjusting one of our numbers from the vector that we created before. Like, how about make it 5, 6, 10? I'm pretty sure that that's not going to be in call A. However, we need to check it with a ref command on the calculator. So let's go ref. I guess the only reason this actually might not be right, this would require A to not span all of our 3 or to not have full rank. So let's see what happens. 1, 4, 7, 5, 2, 5, 8, and 7, and then 3, 6, 9, and 10. Good. It's not in the span of the columns. Maybe a better way to do this though would be to create a situation in A. It worked thankfully for my case, but a better way might be to create A such that the columns we are guaranteed are not linearly independent, and then we could right away know that as long as we choose a B that's outside of that plane, then it's not going to be in the column space of A. Okay, let's look at 29. Okay, 29 says construct a non-zero 3 by 3 matrix A and a non-zero vector B such that B is in null A. Okay, so what we need to do is, I'm going to make my numbers in A a little bit easier. So I'm going to go 1, 0, negative 1, 2, 1, 3, and negative 1, 5, 2. Yeah, that's fine. Okay, so it's possible here that, well, let's see, we need a non-zero vector B, right? Okay, So wait, this means that I would require my columns to be linearly dependent in order for us to get a non-zero vector. So I should probably build this differently. I should probably build this one as 3, 1, 2. Let's go with that. Okay. And by the way, it's okay that there's a 0 in this matrix. A non-zero matrix just implies that all the vectors aren't 0. And we want our vector B to be a member of null A, which means that A times B has to equal the 0 vector. Okay, so let's figure out a B that is full of scalar weights such that these columns are going to, when we take a linear combination of these columns, we're going to get the 0 vector. So here's what we know. We know based on the way we constructed it that A3 is equal to A1 plus A2, which means there's a linear dependence relation that I could write like this. That means that the scalars that I could put on the columns are -1, -1, and 1 to make the 0 vector. So this vector is a member of null A, because if we put those numbers as scalar weights on the columns of A, we get the 0 vector. Okay, 31 is next. All right, respond as comprehensively as possible, justify your answer. I'm probably just going to verbally say the explanation. I'm not going to write it out. Suppose F is 5 by 5, whose column space is not equal to R5. So col F does not equal all of R5. So that means the columns do not span R5. What can you say about null F? Okay, so if the columns don't span R5, that means we don't have 5 pivots, which means at least one column is going to be a non-pivot. So we can say that our conclusion could be that null F does not just equal the 0 vector. Null F is going to contain non-zero vectors. 32. If R is a 6 by 6 matrix and null R is not the 0 space. Okay, so null R is not the 0 subspace. What can you say about col R? So if null R is not the 0 subspace, that means that we have at least one free variable, which means we don't have 6 pivots. So col R is not equal to R3. In other words, the column space does not span all of, or did I say R3? I meant R6. 33. If Q is a 4 by 4 and col Q equals R4, what can you say about the solutions of the equation of the form Qx equal B for B in R4? Okay, cool. So this is linking a lot of ideas together. If col Q is R4, this means that the columns of Q span R4. That means that every vector in R4 can be reached using linear combinations of the columns of Q. So if some random vector B is in R4, there is a solution. So Qx equals B has a unique solution for every B in R4. That's what we can conclude. Because if columns of Q span R4, we are going to have 4 pivot columns, and there are going to be no free variables. We span all of R4, and the columns are linearly independent. All right, 34. If P is a 5 by 5 and null P is the 0 subspace, null P is the 0 subspace, what can you say about solutions of equations of the form Px equals B for B in R5? Okay, so we're interested in Px equals B, where B is a member of R5. All right, well, if the null space is 0, that means that the columns are linearly independent because you have, sorry about the PA announcement. I'll try and just keep going over it. This means that there is a pivot in every column, in every row, so Px equals B is always going to be consistent. So it's really similar to up above. So always consistent. And not only consistent, but there's going to be a unique solution as well. All right, for 35, what can you say about null B when B is a 5 by 4? Null B, B is a 5 by 4. 5 by 4. with linearly independent columns. Okay, if we have linearly independent columns, that means that we have a pivot in every column. But of course, we will have a non-zero row at the bottom because it's a 5 by 4, right? So let's think about solutions to bx equals 0. We can't have any free variables, right? So I'm thinking our answer is that null b is equal to the 0 vector, because the only solution to bx equals 0 is going to be the 0 vector. Yep, that's right. That is right. Let me just confirm that real quick with my solutions. Let me scroll to the right place. Yes, that's right. Cool. Okay, and then 36. Last one. What can you say about the shape of an M by N matrix A when the columns of A form a basis for Rm? Okay, so we're talking M by N, and columns form a basis for Rm. Well, if we have a basis and we span all of Rm, that means we have to have M pivots and N pivots. So the matrix must be square. Right? If we're going to span all of Rm, we have to have a pivot in every row. And if we're going to be a basis, then we have to be linearly independent. So we want a pivot in every column. So if we have M pivots and N pivots, M and N must be equal. Pivot in every row, pivot in every column. So we have a square matrix. All right, I hope those were helpful. I can answer more questions in class if needed.